Hello, my name is Malcolm Griffiths. I'm retired from Chalk River Laboratories and I'm adjunct professor at Queen's University and Carleton University in Ontario, Canada. I'm going to share with you today some of my thoughts on diffraction in the TEM based on the accumulated experience I've had during my career. All of this can be picked up if you read these books, Hirsch, Howie, Whelan, Nicholson, and Pashley. I've taken a liberty here and rearranged the names because I can then call it HHWNP, which is as it was introduced to me when I was a student. More recent book, which essentially takes a lot of what these guys developed back in 1965, apologies, back in 1965, and adds more to it in the context of modern times with modern equipment and advances in understanding. So it takes a lot of what these guys did and puts it in a new book. It was published in 2009. I think there's a second edition out in 2016. I'm not sure. But Williams and Carter, that's a very good book to refer to. And when it comes to defect analysis, my old supervisors here, Loretto and Smallman, they produced a very nice book which is useful for students of electron microscopy who only want to use the fact that diffraction occurs or Bragg diffraction occurs in order to analyze microstructures. Oh, here we go, Bragg diffraction again. Oh, I think this is where, because I'm starting to get more into the theory. Again, just a reminder what Bragg diffraction is: simply superposition of the waves for different conditions, angular orientations of the incoming. Okay, so now we get into the theory. This will be the last part. I introduced, certainly for the case of structure factors, in order to calculate structure factors, that the wave is typically represented by this Euler number. Now, from an academic point of view, the phase, if you like, is some function of the frequency times time, and the distance times some value here, which is a measure of the wavelength or the phase of the wave, and that is 2 pi over lambda. Now, when we talk about electron microscopy, we have a coherent beam of electrons illuminating the sample the whole time. And if you can think about it in terms of a strobe effect, we constantly have this coherent beam which is just there. So in terms of time dependence of the wave, we don't have to worry about it. We're looking at essentially a standing wave, although it's not standing. If you think of it in terms of a strobe, it's a static condition. And so we can forget that. So typically when it comes to electron diffraction and understanding the diffraction effects mathematically, we're generally only interested in the wave number or the wave vector, this k, and the distance. Distance in this case simply being the height within the crystal. One can approximate, even though we're talking about vectors, when it comes down to it, we're only interested in the height, which we call z. So formally, the wave equation describing the amplitude of the electron in the crystal is given by this. It's a sum of the direct wave amplitude and the scattered wave amplitude. So wherever you are in the crystal, you're going to be sampling a bit of both, especially if you're thinking about a column. And why are you doing that? Why would you, even though this is a direct beam, if you like, and a diffracted beam, why do you think of them as being coupled? Because they are coupled. I mentioned in X-ray diffraction how one could think of the diffraction as simply single scattering events. So when an X-ray photon is interacting with an atom and it gets scattered, that's it. You then think about where the X-ray ends up and what the phase of the photon is at the point at which it's detected compared to other photons coming in. In an electron microscope, in a material with electron diffraction, it's slightly different because, well, it's a lot different because the electrons interact so strongly with the crystal that when they're diffracted, they can all then rediffract and then interfere with the direct beam. So what actually happens is that you end up with a coupling of the diffracted wave and the direct wave. So this is the wave amplitudes here are represented by phi, and the wave equation or the phase is represented by this Euler equation here. In this particular case, the deviation from the Bragg condition is represented by Sz. Z is a distance in real space going down the crystal, and S is a distance in reciprocal space, which is the deviation from the diffraction condition. That is the deviation of the diffracting vector of a normal plane and the Ewald sphere. G and R in this case are an additional phase shift caused by distortions in the crystal. It can either come from a stacking fault or a dislocation. So it's the same kind of relation that occurs when you're building up a structure factor based on the position of the atom within a unit cell. But in this particular case, we've already dealt with that. We're already considering that we've got a strong diffracted wave where all of that is taken into account. And then we're looking at other effects now. So deviation from the Bragg condition, as said, and the effect of defects, which in fact change the deviation from the Bragg condition. So, but introduce a phase factor. Now, one of the early attempts to describe this coupling is by representing the diffracted wave amplitude as a combination of the diffracted wave amplitude and some diffracting vector, so that there's some component of the diffracted wave. There's some component of the diffracted wave that feeds back in to the diffracted waves, but there's also the direct wave which feeds into the scattered wave. So this dphi g by dz in this context, relative to the configuration we see here, you'll notice that each component is the denominator. There's this parameter called psi g or psi 0, and this is an extinction length. And this defines the distance in the crystal that the electron is traveling where you might get complete diffraction. Sorry, it actually corresponds to a oscillation in the intensity of which is a full cycle. So we're going from a bright image to a dark contrast, sorry, bright to dark to bright. So this intensity will vary down the crystal. And when there's a maximum amount of intensity which is scattered from the direct wave, we've actually traveled half of an extinction distance. So this extinction distance is a measure of how far the electron travels before it's completely being scattered into some other feature. But then it comes back because of the coupling with the diffracted beam. So you can see how, if we look at d-phi, the change in the amplitude, let's say of the direct beam or the scattered beam, the change in the amplitude is if you like, is dz over psi g. It happens over a certain distance where you get a change for whatever reason. You get some change in the amplitude because of diffraction effects, which are dictated by and the distance over which this occurs. Like say 100% distance is psi g, and dz says what fraction of this 1 over psi g we're considering at each step as we proceed down the crystal, through the crystal. Now it turns out that when Hirsch, Howie, Wheeler, Nixon, and Pashley wrote their book, in it they make the point that they can't get this equation to work. It doesn't give the variation in electron intensity as a function of either deviation parameter or distance in the crystal, or that one would observe. So it didn't match observations, and it didn't lend itself to easy solutions. And what they found was that they could get agreement with the observations by applying a modification to this, and this is the modification that they applied. They, in effect, split the amplitude into a real and an imaginary part of different amplitudes, because you have different extinction lengths that are in the imaginary component. So they found that they had to do this in order to get the agreement with what's observed. And what are we talking about? What's observed is the variation in the intensity as you go down the crystal for different combinations of these extinction distances, and also the variation as one moves between S positive and S negative. So, and this is directly from Hirsch, Howie, Wheeler, Nicholson, and Pashley. In order to solve the equation, what they did is they made some substitutions, some phase shifts to simplify the solution, and they ended up by simplifying these equations into this form in terms of the Howie-Wheeler equations, but the Hirsch, Howie, Wheeler, Nixon, and Pashley equation, it becomes in a simpler form like this. You'll notice that the S and the deviation from G, or the scattering effect of defects, dislocations, and stacking faults, it's not, when you make these substitutions, it's extracted from the exponential form, and it just becomes a multiplier in this particular case to some new wave amplitude. So taking this equation, we then want to look at the solution to this equation. And you can do this numerically. So in my case, I used MathCAD. I plugged it into a Runge Kutta routine. Where, oh, look at that. This is cut off here. Where this array here represents the starting conditions for the real part of the direct beam, the imaginary part of the direct beam, the real part of the diffracted beam, and the imaginary part of the diffracted beam. And within MathCAD, there is the Runge Kutta routine. Using the Runge Kutta method allows one to step through, take incremental, if you like, an iteration, change the dz, change the depth a little bit, and then calculate at each point a new factor which feeds into this array. And but how these different components, the real imaginary parts, how they change depends on the other entries. We have the real and imaginary parts of the direct beam and the real and imaginary parts of the diffracted beam. These parts contain the effect of the dislocation. In this particular case, sorry, I've included a dislocation, and this is the equation that defines what the rotation of the dislocation planes, the effect of the strain from the dislocation has on the phase factor. And here we have the deviation parameter. So when you do it this way, we can, and this is for a simple case of a screw dislocation. And that's in Hirsch, Howie, Whelan, Nicholson, Plashley. So anyway, you can solve those equations numerically, not analytically, numerically, and get something like this. So these are the two cases, S negative, S positive, just with some random selection of parameters which seem to work. And then if I put in a dislocation at the location 50 units in the thickness, this is an arbitrary length scale, 0 to 100 units, we see the effect on the scattered intensity. So that's one way to do this, the solution to the equation. But as I mentioned earlier, the one can think of the waves or the wave amplitudes for both the direct beam and for the scattered beam as being like a standing wave, or a wave which is, you turn the strobe on and you're freezing it. So the time is factors out, and we're just looking at the distance. But in doing that, we can come up to a solution because it's a static solution for those wave equations. Now it turns out for the defect-free, let's not complicate it now, it's for the defect-free case where there's no dislocations or stacking faults. By manipulation, by substitution of the Hirsch-Howie equations, it's possible to create a differential equation for each wave, for the amplitude of the direct wave and for the amplitude of the scattered wave. And these equations are analogous to what you would get from a coupled oscillator. And basically, because it's essentially somewhat like a coupled oscillator, you have a wave coming in, some gets scattered, some doesn't, some gets diffracted, some of that diffracted wave gets scattered and some doesn't. And then you look at down this column, you approximate to look at what the effect of varying Z has on the amplitude of these things. In Williams and Carter, and I think the same also applies to Hirsch, Howe, and Whelan, they use the ansatz method to solve these equations. They use basically a complex exponential. They assume that this wave vector is now a complex exponential. And that gives two solutions for each oscillator. So we can think of it pictorial like this. Here's a coupled oscillators. I pulled this off the internet. And you can see how if we think about a direct wave and the diffracted wave, and they're going down through the crystal, this is as a function of time, but in our case it was a function of distance in the crystal. These waves are sharing energy back and forward, and the amplitude is varying accordingly. And that's the coupling. That's the coupling effect. Now this is a mechanical oscillator, coupling of a mechanical oscillator, and it's not quite so simple for us in diffraction because we have these scattering events which change the phase, and it's not exactly like this. On top of that, the other complication is refraction. Now, when electrons are passing through a material, some of them may be slowed down by the repulsion from other electrons, and that slowing down reduces their wavelength, increases their wave vector. But some of them may be speeded up when they're attracted by the atomic nuclei. So what you end up with is the possibilities of getting two waves. Well, sorry, I shouldn't say two waves. Yes, two waves. And you can think of that in terms of how these waves would then interact, the one being slowed down and the one being speeded up. We also then end up, if you superimpose two waves which have slightly different wavelengths, you end up with somewhat similar to this, a situation like this, for which there are two solutions for the wave equation. So you're essentially plugging this thing into that and coming up with a more complicated result. So while a pair of coupled harmonic oscillators serve as a good mechanical analog for kinematical electron diffraction, I didn't mention that it was kinematical, but that's single events, if you like. Dynamical, actually, I'm not even sure that that's correct. Let's just say it's a reasonable mechanical analog. Dynamical diffraction is complicated due to dispersion, because the electrons entering the crystal are scattered, refracted in two possible ways. The electrons are either decelerated or accelerated by the potentials in the crystal. The direct and diffracted waves are then the result of interference of the two resultant waves of different wavelengths. So in a non-dispersive medium, or if we're thinking about kinematical electron diffraction, we don't consider the formation of anything of these refracted waves, there's no refraction and weak scattering. And this is how the diffracting vectors would be envisaged in an Ewald sphere construction. You have a beam represented by a wave vector, which is 1 over the wavelength, and then it's diffracted. And the difference between the two beams is the diffracting vector G. Not to assimilate there. But when we think about dispersion, there are two possible waves now. We've created this slowed wave, which has a shorter wavelength, and in terms of the reciprocal space, this amounts to a larger vector for both the direct and the diffracted beam. We have a larger vector than what would be the case for the kinematical case, where you have no dispersion. So these two waves, when you're close to Bragg, are coupled, and we have an interaction. So we have a number of possibilities. We got the direct, so the refracted, what's called a Bloch wave 1, refracted Bloch wave 2 in the direct beam, and then the same, but with this deviation from the diffraction effect, the diffracting vector of G in the diffracted case, which then are summed up, superimposed to give what would be the diffracted intensity. And likewise, if we were looking at the direct intensity, it's the sum of these two waves as they are selected on the backfocal plane of the microscope. So Bloch waves are a natural consequence of refraction, but they're also a natural consequence of what Hirsch, Howey, Wheeler, Nicholson, Pashley, how they formulated their equations. But remember, Hirsch and company, they had to assume some fudge to make the equations work with no physical relationship. It's just some way to make the equations give you the answer you want. And then when they work through the formulations, it turns out that they had to have two solutions to the wave equations, or multiple solutions, two solutions for the direct beam and two solutions for the diffracted beam, which is exactly this. But that's what one would come up with anyway if one was just simply did a thought experiment and say, what do we have if when our wave coming into the crystal is refracted, but it's refracted into two parts? How do these different two parts then interact when it comes to this coupling effect of the direct beam and the diffracted beam? And this is a pictorial picture. Of course it's a pictorial picture. This is the way to think of it in a non-mathematical term. But we end up with this anyway, or Hirsch and company ended up with this picture because they had to apply the fudge factors to make the equations work in the first place. So when I was first introduced to dispersion surfaces and this sort of thing, I didn't understand it. As a student, physics at Bristol University at the Royal Fort, we had a lecturer, his name was A.R. Lang, Professor A.R. Lang, and the first lecture we had, we were introduced to these things. He came in and he drew a circle on the board and he drew another circle on the board and said, there's a dispersion surface. And then he proceeded to just talk at the board for the next half an hour, mumbling something about dispersion and diffraction and whatever. And we were all scratching our heads. We go, what the heck is he talking about? And I've never really understood Bloch waves until more recently. And then it occurred to me that, oh, we're talking about two real waves, and they can be detected. And this is an image of a Bloch wave, an electron diffraction that I pulled off the internet. They can be detected, and they're real. There are real waves. And once you realize that they're real and they're not some imaginary number, then it becomes much more, or a fudge factor, if you like. Then it becomes much more poignant, and one can understand it and accept it much easier. And if I have to share anything with you, it's that. And I might be wrong. I could be completely out of my mind, but this is how I can rationalize it. The only way I can rationalize everything that Hirsch and company did and put it in, make it sort of make sense physically, is if I start off by thinking in terms of, well, we got two possible waves here, or two refracted waves, and they can each interact both by being coupled to give a diffracted beam, and yeah, so we end up with this range of possible solutions. The Bloch wave 1 has a larger wave vector, and that's a shorter wavelength because it's slowed by the medium. And Bloch wave 2, which is this bottom one, has a smaller wave vector. It's a longer wavelength because it's accelerated by the medium. So how does this work out formally? Well, we go from representing, as I showed you initially, the wave equation in the crystal being represented by this. It's now represented by a sum of Bloch waves with different multiplying factors. So the Bloch, we have different, these amplitudes, if you like, are a function of the deviation parameters. But Bloch wave 1, so for whether you talk about, I should mention that this really is for, yeah, so Bloch wave 1 is some combination of these diffracting conditions. Bloch wave 2 is given by that. So these are the solutions to the differential equations which were put together in order to fit the observations. Okay, so the two Bloch waves have wavelengths which are greater and smaller than the incoming waves. I've mentioned that already, so I don't have to talk about that anymore. Okay, so finally, the last point I want to make is in textbooks, you'll see this kind of representation of the Bloch waves. Bloch waves corresponding, in this case, it's the 1 and the 2 here. So we have Bloch wave 1, which is the one that's slowed, and Bloch wave 2, which is the one that's speeded up. So traditionally accepted, Bloch wave 1 is the one that's absorbed the most for negative deviation from the Bragg condition. And it's generally assumed that's because this is the one that interacts with the atomic nuclei and is therefore more absorbed for this S negative condition. While it's traditionally assumed that Bloch wave 2 is the one traveling down between the atom nuclei. But I'm not so sure that this is the right picture. Is it correct? Well, according to what I just explained there, where I could think of Bloch wave 2, which is the smaller wave vector and therefore larger wavelength, this would come about physically. You can envisage what Bloch wave 2 is about by it being accelerated. And Bloch wave 1 is the one that's decelerated when it comes into the crystal. So what I think is probably a better picture is this one is the one, Bloch wave 2 is the one that's going close to the atomic nuclei and is being accelerated, but it's not being absorbed by the nuclei. I mean, the nuclei themselves, physically, the cross-section is very small. So it goes whizzing past, like a gravity assist, if you like. And we end up with little absorption, but we do get the slowing effect for Bloch wave 2. Now, whereas Bloch wave 1 is, let's say it's traveling through the electron cloud surrounding the atomic nuclei, and it is absorbed. The reason to think of this as being the more feasible picture, being absorbed, is absorption is a bit of a misnomer, because in the context of an electron microscope, if you have a big thick piece of material and you shine electrons through it and the image is just basically dark, it's not because the electrons are all sopped up by the material. It's because the electrons are scattered out away from the optic axis. They're scattered into the sides of the microscope. So absorption in that context is really more scattering. And I could rationalize that in this picture simply by saying the nuclei are very small, and therefore you get less scattering, but more acceleration. But here, when the Bloch wave is traveling down between the planes of the atoms within the electron cloud, which is the bonding electrons, the valence electrons, and the bound electrons, and the bound electrons as well. Whatever, you've got a lot more events happening, a lot more scattering events, and therefore more absorption happening here. So we end up with these two equations, essentially that lead you to this picture of the two Bloch waves in the crystal. And that comes about because we had to make, or Hirsch and company had to make certain assumptions about the equations and how they could manipulate them or reformulate them or make them agree with the experiment. So they become, in effect, empirical equations. So to finish now, I'm just going to read this. Electrons traveling in a crystal potential can be represented by simultaneous equations that are similar to the mechanical analog of coupled oscillators. This inevitably results in a solution for the two oscillators, the direct and diffracted waves. That is a combination of the two solutions for each quadratic equation derived for each oscillator. The coupled simultaneous equations describe what is observed and imply that there are two solutions, Bloch waves, that can be combined to describe the variations in amplitude of each oscillator. But which came first? If one looks at the equations that are formulated, we end up with two Bloch waves being the result. But which came first? Refraction acts on the direct and diffracted beams, producing two separate real electron waves that then travel through the crystal. The description of the total electron intensity is the function of scattering angle and distance traveled in terms of coupled equations follows. So you going at it from the reverse direction, you'd get the same answer. My math isn't good enough my brain hurts too much to to try and do that. But I'm just sharing with you a way I can rationalize this. It helps me understand what's going on. And when I just take things on faith, as I have had to do over many years, before I realize, maybe these waves are actually real waves. Once I realize that for myself, I can accept this, and it doesn't frighten me anymore. So I like the idea of the two refracted waves, and I like the idea that we aim to that solution by two separate routes. In the one route, which is the one that I can handle, is the physical consideration of refraction, and the other route is by making these what in effect turns out to be empirical solutions to fit the observations. One ends up at the same picture, that you have to have, in effect, two waves for each wave vector in the crystal, one being the direct wave vector and the diffracted wave vector. They're each separated into two components, which are from Bloch wave 1 and Bloch wave 2. And you couple them all together, and you, by some further manipulation, you can rationalize what you get. I'm comfortable with that. Okay, so this came from a lecture I gave recently, which shows some. It's just some things from YouTube that I put together, showing slip and defects in crystals. But the bottom one here is of value because it's something I saw on YouTube, which explains the refraction, especially with electrons. So it's a good one. And that's all I have to say now. Thank you. What I've done recently is created a book, An Engineer's Guide to Nuclear Core Materials. And in chapter 4 of that book, I talk about characterization of microstructures. And I didn't want to get into too much detail when it comes to the theory of diffraction in the TEM, especially the TEM, although I do cover X-ray diffraction quite extensively. I make the point that transmission electron microscopy using electrons or electron diffraction is more complicated than X-ray diffraction because of the interaction of the electrons. They're charged particles, waves that interact much more strongly with matter than do X-rays. So I thought I would follow up and actually give you my thoughts on electron diffraction and how it should be treated. Okay.